This second problem related to the transverse and radial components actually deals with the second method, the one that takes an expression of r as a function of theta and then applies the chain rule to get r dot, r double dot, and then replace that in the equation. So here we have a searchlight, as you can see in the image on the right, which casts a spot of light along the face of a wall that is located 100 meters away. We're asked to determine the magnitude of the velocity and acceleration at which the spot appears to travel across the wall at the instant theta is equal to 45 degrees. The searchlight rotates at a constant rate of theta dot is equal to 4 radians per second. So I'll give you a couple of minutes to try to solve this one on your own. Remember, you need to find an expression of r as a function of theta and then apply the chain rule to get the values of r dot and r double dot. Now I know this problem is really complicated at first, so I do not expect you to solve it on your own. Whenever you feel like you're ready to see the solution, simply continue the video. In step 1, we need to write down what we know first. So we have the distance, d is equal to 100 meters. We have theta dot is equal to 4 radians per second. And we know that we're dealing with the transverse and radial framework, in which we're given theta dot is equal to 4. So we have a value for theta and theta dot, and we do not have any expression of r as a function of time or theta as a function of time. So we're clearly dealing with the second method, in which we need to find r as a function of theta. To do that, let's move to step 2. From the figure and using simple trigonometry, one can note that r, which is the radial distance from the searchlight to the wall, is equal to 100, which is the vertical distance, divided by cosine theta. And theta is the angle between the ray of light and the vertical. So now that we have an expression of r as a function of theta, we can move to the third step, which is the most complicated step, in which we need to make use of the chain rule to find r dot and r double dot. But before we dive into actually performing the chain rule operation on that expression, I would like to mention a couple of words about the chain rule. So in simple terms, the chain rule allows one to take the derivative of one parameter, let's say x, with respect to another parameter, let's say t, when x is written as a function of a third parameter, y. And in this case, the third parameter y is also related to t. So let us write that down in terms of an example. So let's say we're given x as a function of y, which is equal to 3y squared. And we're asked to find x dot, which is dx over t, when y is actually a function of time. So y is equal to 5t cubed. Again, I would suggest you read again the statement above and compare that to the actual example and see how it all makes sense. And then once you've understood what I've just explained, you can move forward with the video. So now that we know when to use the chain rule, it is time to see how to use it. So we want to find dx over dt, and we know that x is a function of y, and y is a function of time. So at the end of the road, if you write down x, y, you get t. So doing all the replacement, you have x as a function of time. But to take the derivative of x as a function of time is not as easy as before. Now we can write that dx is equal to dx over dy times dy over dt. So this is the most important step in the chain rule expression. So basically what we're doing here is that we're splitting the expression, numerator and denominator, and adding an intermediate variable, which in this case our intermediate variable is y, since x is in terms of y, and we're looking to a derivative of x with respect to time. So y is clearly the intermediate parameter here. So we add y, or actually dy, on the numerator of the second term and the denominator of the first term. And intuitively, you can simply take off dy and dy, and you'll come back to the initial equation, which is dx divided by dt. So now that we have those two values or expressions, dx over dy and dy over dt, we can simply perform the derivative for both of these terms. So the derivative of the first term, dx over dy, well, since x is equal to 3y squared, the derivative of that with respect to y is equal to 6y. So 3 times 2 times y. Next, we need to find the derivative of y with respect to time. Since we have an expression of y in terms of time, y equals to 5t cubed. The derivative of that with respect to time is equal to 15t. Then multiplying the two expressions, dx over dy and dy over dt, one has 6 times 5 times 15 times t to the power 4. And so that's exactly how you can calculate the derivative of x with respect to time when x is actually a function of y, which in turn is a function of time. So remember, at the end of the road, when you do all the replacement, the variable t needs to appear. But the way to calculate the derivative of x with respect to time is by applying the chain rule. You cannot simply take the derivative of the final expression 5t cubed with respect to time to get the answer. I highly recommend you guys go over this slide again, read the statement about the chain rule, then try to solve the example problem on your own. And once you've understood how the chain rule actually works, you can move on and watch the rest of the video. So now that we know how to apply the chain rule, let us do that for the expression at hand. So we have dr over dt that we need to find, so that's r dot. And we know r as a function of theta and theta which is a function of time. So to apply the chain rule here, we can add the d theta components in the numerator and denominator. So we have dr over d theta times d theta over dt. Now it is always a good practice to split the two terms from the right hand side and work out each of these terms on their own. So for dr over d theta, we can replace r as a function of theta, so that's 100 divided by cosine theta, and simply take its derivative. Again, remembering from calculus, we're dealing with the fraction, so we can write u is equal to 100 and v is equal to cosine theta. U prime is equal to 0 since it's a constant, and v prime is equal to minus sine theta. And we know that the derivative of a fraction is u prime v minus v prime u divided by v squared. And so doing all that replacement, we end up with a value for dr over d theta, which is tan theta divided by cosine theta times 100. So that's for the first term of the right hand side. Let us work out the second term of the right hand side, which is d theta over dt. Now obviously the derivative of theta with respect to time is written as theta dot. And if you look back at the problem's given statement, we know that theta dot is equal to a constant, which is equal to 4 radians per second. So now that we have the two terms, we can multiply them together and get a final value for dr over dt. So dr over dt, which is equal to r dot, is equal to 400 times tan theta divided by cosine theta. So that's great. We're able to use the chain rule to get r dot. Now let us use the chain rule to get r double dot, which is d2r divided by dt2. Now the more you go into the derivations, the harder the chain rule gets. So in this case, we have d2r divided by dt2. Now if we split that into two derivatives, we can write that as d over dt of dr over dt. And since we have already computed dr over dt, we can replace that here. So that's 100 tan theta over cosine theta times theta dot. Remember, whenever you're taking the derivative with respect to a specific variable, you should always keep the variable and all its derivatives in their general form. So you should not replace them with the actual value you attributed them. So here, for instance, we know that theta dot is equal to 4. So one might replace theta dot with 4, but that's wrong. You should always keep all the variables as variables, because you would need to take their derivatives later on. So here we keep the value of dr over dt as 100 times tan theta divided by cosine theta times theta dot. And now we're asked to find the derivative of that expression with respect to time. So you can notice here in the expression that we we actually have the product of two terms. On the first side, we have 100 times tan theta divided by cosine theta. That's the first term, times the second term, which is theta dot. So we're clearly faced with the derivative of the form u times v. And so the derivative of that is u prime v times v prime u. And so it's d over dt over 100 tan theta divided by cosine theta, that's the u prime, times v, which is theta dot, that's the first term, plus v prime, which is theta double dot, times u, which is 100 times tan theta divided by cosine theta. So you can clearly see that the derivative of the product is the sum of two terms, u prime v, which is here labeled by 1, and v prime u, which is labeled by 2. And so since we're adopting a systematic way of solving problems, let us develop each of these terms on their own. So now tackling the first term, which is d over dt is equal to 100 tan theta divided by cosine theta times theta dot. We notice that we want to find the derivative with respect to time to an expression that's related to theta. So we need to apply the chain rule here as well. So adding d theta in the denominator and the numerator, we get d over d theta of the whole expression, 100 tan theta divided by cosine theta, times d theta over dt times theta dot. So you can clearly see here that we've added d theta in the denominator and the numerator. Now we need to find the derivative with respect to theta of 100 tan theta cosine theta. Now we can see that it's in the form of u divided by v, where u is equal to 100 tan theta and v is equal to cosine theta. And u prime is therefore equal to 100 divided by cosine squared theta, and v prime is equal to minus sine theta. If you do not know how I've got u prime and v prime, you can simply check any reference book on derivatives. So now that we know what u prime and v prime are, we can expand and get the derivative with respect to theta of 100 tan theta cosine theta, and we would get the expression which is shown here, times d theta divided by dt, again, times theta dot. And now noticing that d theta over dt is equal to theta dot, we clearly have theta dot times theta dot, and that's theta dot squared. Again, simplifying the first term, we'll end up with the expression shown here. So we were able to expand the first term. Let us now expand the second term. So it's 100 tan theta divided by cosine theta times theta double dot. Now since theta dot is equal to 4, it's a constant, we do expect that the second derivative, or theta double dot, would be equal to 0. And so the second term is actually completely equal to 0. Now we can go back to the general expression for d2r over dt2, and setting the second term to 0, we end up with the following expression. Now we can finally replace theta dot and theta with 4 and 45 respectively, and then we'll get the final value for d2r over dt2, which is equal to 6788.2. Let us now nicely summarize all the different variables we have computed or can compute now. So we have d2r over dt2 is equal to 6788.2. dr over dt can be obtained by replacing theta with 45. This gives us dr over dt equals to 565.7. And r can be computed by replacing theta equals to 45 as well, which gives us r equals to 141.4. We also know that theta dot is equal to 4, theta double dot is equal to 0, and theta is equal to 45. Now finally, for step 4, we can replace all these variables in the equations for v and a. So for v, we have vr ur plus v theta u theta, which is equal to r dot ur plus r theta dot u theta. Replacing all the variables here, we end up with v is equal to 565.7 ur plus 565.7 u theta. To compute the magnitude of v, we can simply take the square root, which gives us v equals to 800 meter per second. Similarly for A is equal to AR UR plus A theta U theta, replacing the variables AR and A theta by their respective expressions, and the variables R double dot, R dot, theta dot, and theta double dot with their values, we end up with A equals to 4525.5 UR plus 4525.5 U theta. To compute the magnitude of A, we simply take the square root again, which gives us A equal to 6,400 meter per second square. Now I know this problem took us long, but I really want you to understand the different steps we went through to solve this problem and how we actually made use of the chain rule, no matter how complicated the expressions were. So I highly recommend you guys go back and solve the complete problem on your own. And whenever you feel that there's something you did not understand well from the first time, you can clearly watch the video again. It is very important to understand these steps because any problem that deals with the second method for a transverse and radial component would actually require you to apply the chain rule once to get dr over dt and twice to get d2r over dt2.